So, the Webb is going to be able to look at planets that we've discovered around distant stars in the vast puzzle of our universe. The James Webb Telescope is finding pieces we didn't even know existed, shaking up everything we thought we knew. Could our laws of physics be in for a rethink? Is our universe textbook due for an update? Renowned physicist Brian Cox is stepping up to share his thoughts on these earth-shaking revelations. Join us as we're about to journey through the astonishing wonders of the cosmos like never before. Stay tuned and prepare for a cosmic voyage of discovery. Okay, are you ready for a cosmic story? Picture it, Christmas Day 2021. While most of us were unwrapping gifts and sipping hot chocolate, the world of astronomy was getting the biggest present of all, the launch of the James Webb Space Telescope, or JWST for short. And let us tell you, this isn't your run-of-the-mill telescope. It's the biggest, baddest optical telescope we've ever put in space. It's packing a colossal primary mirror that's 6.5 meters across. Now, the JWST isn't just hanging out up there for the view. Its mission? To cast its superpowered gaze back in time, studying the first galaxies that appeared in our universe. It's like a cosmic detective, unraveling mysteries about the birth of stars and planets. How does it do all that? Well, it's kitted out with 4 scientific instruments. There's the near-infrared camera, or NIRCam, the near-infrared spectrograph, also known as NIRSpec, the mid-infrared instrument, shortened for MIRI, and the fine guidance sensor near-infrared imager and slitless spectrograph, aka FGS NIRIS. It's a mouthful, we know, but these are the tools it uses to peek into the atmospheres of distant exoplanets. And here's something that'll blow your mind. The JWST is so far out in space, orbiting around the Sun, that it's about 930,000 miles away from Earth. And at that distance, things get chilly. We're talking minus 223 degrees Celsius kind of chilly. Now, this impressive mission isn't a solo act. It's the result of an epic collaboration between NASA, the European Space Agency, and the Canadian Space Agency. So next time you look up at the night sky, remember, the JWST is out there, unveiling the mysteries of our cosmos. Isn't that something? You know how we're always wondering if we're alone in the universe? Well, we've been doing more than just wondering. We've been peeking into the celestial depths with telescopes, uncovering secrets hidden light years away. Let's take a journey through the cosmos, shall we? Our destination, TRAPPIST-1b, an exoplanet that's been a real game changer in our cosmic understanding. So first off, what's TRAPPIST-1b? It's a super-Earth exoplanet, which is essentially an astronomy way of saying it's kind of like Earth, but, well, super. It's not Superman or anything, but it is larger than our home planet. In fact, it's about 1.37 times the mass of Earth and 1.12 times the radius. But despite its size, it's still smaller than the likes of Uranus and Neptune, our system's ice giants. Now, where is this fascinating world? It's part of a family of 7 rocky planets, all orbiting a pretty unique star called TRAPPIST-1. And where's that, you ask? It's in the constellation of Aquarius, about 40 light years away from us. That's pretty far by our standards, but in cosmic terms, it's almost like being neighbors. The way TRAPPIST-1b was discovered is quite a fascinating story too. A team of astronomers, peering through the lens of the Transiting Exoplanet Survey Satellite, TESS, and Planetesimal's small telescope, TRAPPIST, based in Chile, first spotted it in 2016. This was also made possible with the help of several other ground and space-based telescopes. One interesting aspect of TRAPPIST-1b is how close it is to its star. It orbits at a distance of only 0.0115 astronomical units. If that seems like gibberish, imagine it this way. It's around 30 times closer to its star than Mercury is to the Sun. Because of this, it whips around its star in a super fast orbit, completing one cycle every 1.5 days. This speed means the planet is tidally locked, which is just a fancy way of saying one side always faces the star, while the other side constantly faces the cold void of space. Now, this super close orbit means that TRAPPIST-1b gets quite the suntan. It receives about 4 times as much radiation as Earth gets from the Sun. As a result, the planet is pretty toasty. If you were standing on the surface, which, by the way, you really wouldn't want to do, the temperature would be around 227 degrees Celsius, or 440 degrees Fahrenheit. The James Webb Space Telescope played a crucial role in learning about TRAPPIST-1b's temperature. It used its impressive mirror to detect the faint mid-infrared light from the planet, something that was extremely challenging given that the planet is a lot dimmer and closer to its star. But by employing a special technique called chronography, the telescope managed to block out the majority of the starlight and reveal the planet's signal. By measuring the thermal emission of the planet, which is essentially the heat energy given off in the form of infrared light, scientists were able to directly measure the temperature of this rocky exoplanet for the first time. Their measurements also suggested that TRAPPIST-1b doesn't have a significant atmosphere. This could be because it either lost its original atmosphere due to the star's intense stellar winds and ultraviolet radiation, or maybe it never had one in the first place due to its formation history. The discovery of TRAPPIST-1b, along with its 6 sister planets, was nothing short of a revelation in the field of exoplanet research. It showed that rocky planets could form around very low-mass stars, which are the most common types of stars in our galaxy. This opened up new possibilities for studying the diversity and evolution of planetary systems, as well as potential signs of life on other worlds. But that's not the only insane discovery, and some of these discoveries are making us question everything we have ever known. 2 galaxies have been causing quite a stir in the world of cosmology: Glass Z12 and Glass Z10. 2 truly extraordinary galaxies. They are like cosmic celebrities. Given they're among the most distant and luminous galaxies we've ever seen, they date back to mere 350 and 450 million years after the Big Bang. Now, you might be wondering who or what found these galaxies. The answer is the James Webb Space Telescope, which is quite a marvel. It discovered Glass Z12 and Glass Z10 in July 2022, thanks to a program called the GRISM Lens Amplified Survey from Space, also known as GLASS. That's quite a mouthful, isn't it? But it's basically a program that uses something called gravitational lensing to magnify the light from extremely distant galaxies. So what is this gravitational lensing thing all about? Well, it's a bit like using a magnifying glass, but instead of glass, you're using the gravity of massive galaxy clusters to enlarge or magnify the light from galaxies located way in the background. In this case, one of these magnifying glasses is a Bell 2744, also known as Pandora's cluster. This cluster is located about a staggering 3.5 billion light-years away. The JWST images of a Bell 2744 revealed 2 seemingly insignificant little red dots among a sea of hundreds of other galaxies. But these red dots were anything but insignificant. They indicated that these galaxies were extremely far away, and that their light had been stretched by the expansion of the universe into the infrared part of the spectrum. To figure out just how far away these galaxies were, astronomers estimated something called their photometric redshifts, which is a bit of a complicated term that basically refers to an estimation of how far away something is based on its color. It turned out that the estimated redshifts for Glass Z12 and Glass Z10 were about 12.4 and 10.5, respectively. Now, these numbers might not mean much to us, but in astronomy speak, they translate into distances of approximately 13.6 and 13.4 billion light-years. In other words, when we look at these galaxies, we're looking at light that has traveled for about 350 and 450 million years after the Big Bang. Mind-blowing, isn't it? To confirm these redshifts and distances, the astronomers needed to do something called spectroscopic observations, which is essentially a fancy way of saying they needed to measure the wavelengths of specific emission lines from the galaxies. For this, they turned to the Atacama Large Millimeter Submillimeter Array, also called ALMA, a collection of radio telescopes based in Chile. These guys detected an emission line associated with something called doubly ionized oxygen at 258.7 gigahertz from Glass Z12. This line confirmed that Glass Z12 has a spectroscopic redshift of 12.117, making it one of the earliest and most distant galaxies we've ever discovered. Now let's delve into the topic of star formation. The O3 emission line also allows astronomers to estimate the star formation rate, also called SFR, of Glass Z12. In simple terms, the SFR is a measure of how quickly a galaxy is producing new stars. And you wouldn't believe it, but the SFR of Glass Z12 is about 100 solar masses per year. That's very high for such a small galaxy. In layman's terms, Glass Z12 is like a cosmic factory working overtime, churning out stars with incredible efficiency and speed, and likely burning through its gas reserves in a relatively short time span. Now, dive into why the discovery of Glass Z12 and Glass Z10 holds such substantial implications for our understanding of how galaxies formed and developed in the early universe. These galaxies are effectively throwing a curveball at our existing theories and models that we use to explain how cosmic structures develop over time. Let's first look at the theory known as hierarchical structure formation. This idea proposes that the universe is kind of like the world's biggest Lego set. Smaller structures merge together to form bigger ones as time progresses. According to this theory, heavyweight galaxies like our own Milky Way should be the result of lots of these mergers over time, and should form later than smaller ones like Glass Z12 and Glass Z10. However, it seems these baby galaxies, though small, have formed as many stars as our present-day Milky Way in a relatively short time. This implies they are incredibly efficient at transforming gas into stars, suggesting that there could be other processes at work in the early universe, such as feedback from supernovae or black holes, or perhaps the initial conditions of the gas were different from what we had presumed. We also have another theory called cosmic reionization. This theory explains how the first stars and galaxies ionized the neutral hydrogen gas that was filling the universe after the Big Bang. We believe reionization occurred between 400 and 800 million years after the Big Bang, and was typically attributed to the ultraviolet radiation from the first stars and galaxies. But here's the twist. Glass Z12 and Glass Z10 are so bright and massive that they could have made a significant contribution to reionization by themselves even at earlier times. This suggests that reionization might have been more complicated and variable than we previously thought, and it indicates that our models of how it occurred may need some revisions. These discoveries also mean that there's now a whole new realm of possibilities for exploring the early universe with tools like JWST and other telescopes. We're just scratching the surface of what JWST can reveal, since it has only observed a small fraction of the sky so far. Who knows? There might be many more galaxies like Glass Z12 and Glass Z10, or even more distant and exotic ones, waiting to be discovered. Plus, JWST can further study these galaxies in more detail using its spectroscopic capabilities to measure their physical properties and evolutionary histories. This will hopefully help us answer some of the fundamental questions about how the first galaxies formed, how they influenced their environment, and how they led to the diversity of galaxies we see today. However, some people don't think it's all doing us a favor, but making us ask more questions. Let's bring in a 2022 paper by Naidu et al. Titled, "Two Remarkably Luminous Galaxy Candidates at Z, Approximately Equal Sign 10 to 12 Revealed by JWST." This study suggested that galaxies such as Glass Z12 and Glass Z10 would be difficult to explain within the standard cosmological model, and might require new physics or revisions to existing theories. Let's talk about the mammoth task that is the detection and confirmation of such distant galaxies. Imagine trying to spot a single grain of sand at the bottom of the ocean from the surface. That's the level of difficulty we're dealing with here. These galaxies are extremely dim, and there's a ton of matter along our line of sight obscuring them. Plus, accurately determining their distances is a whole other game, and it's not an easy one. This part requires interpreting the galaxy's spectral energy distributions and photometric redshifts, a bit like trying to understand an alien language. These methods essentially translate the light received from these galaxies into meaningful data that can hint at their distance. But like any translation, it can be influenced by many uncertainties and assumptions. Everything from the models we use, the filters we apply, and the methods we utilize can impact our interpretation. To top it all off, the standard cosmological model, our theoretical framework for understanding the universe, didn't exactly predict such distant and bright galaxies. It's a bit like planning a party for 10 people, and suddenly 100 people show up. It's unexpected and a little hard to handle. According to our model, at such high redshifts, the number of bright luminous galaxies should be low, a lot like expecting to find very few fully grown trees in a newly planted forest. This paper really took our understanding of galaxy formation and evolution in the early universe and gave it a bit of a shake. We now have these two galaxy candidates sitting at the edge of the cosmic frontier, a bit like interstellar explorers, challenging our standard cosmological model and potentially opening doors for new physics or tweaks to our existing theories. Now, these aren't just any old claims the paper is making about them. They've got some compelling reasons and data to back up their bold statements. Firstly, Naidu and the team assert that the detections of these galaxies are solid, not some cosmic flukes or interlopers from lower redshifts just masquerading as super old galaxies. A few key characteristics of these galaxies play into this confidence. Firstly, both galaxies have a distinctive break, or sudden drop in their spectral energy distribution around the 3-micron wavelength mark. If you're scratching your head about what that means, picture the light from the galaxy as a line graph of different wavelengths. At 3 microns, the line takes a nosedive, indicating less light is coming from the galaxy at those wavelengths. This is consistent with what you'd expect from a high redshift galaxy due to something called the Lyman alpha break. The Lyman alpha break is a phenomenon where light with wavelengths shorter than the Lyman alpha line, a specific emission line from hydrogen atoms, gets absorbed by the neutral hydrogen that's just hanging out between galaxies. This feature is hard for lower redshift sources to fake, which adds weight to the galaxies being at such a crazy distance. Another point in their favor is that these galaxies are like cosmic ninjas. Below 3 microns, they aren't detected in those bands at all. Usually, you'd expect some light from lower redshift sources in this region. The absence of it here rules out the chance that these are quiet galaxies with strong Balmer breaks or dust-ridden star-forming galaxies, both of which can sometimes play cosmic chameleons and look like something they're not. These galaxies are also pretty loud, in an astronomical sense, of course. They have a high signal-to-noise ratio in multiple bands above 3 microns, meaning the galaxy signals stand out clearly from the usual background noise. This suggests that we're not dealing with spurious sources or random noise blips, but actual physical celestial bodies. The paper goes on to make an even bolder claim. These galaxies don't just exist. They're causing a stir in the standard cosmological model, enough to potentially necessitate new physics or theory revisions. Here's why. The luminosities of these galaxies are off the charts, with absolute UV magnitudes of around m_UV, approximately -21. This hints at a blistering star formation rate, about 100 times the mass of our Sun each year. In the language of the cosmos, that's akin to popping out a new star every few days. This level of stellar productivity is a bit eyebrow-raising for such high redshifts because the universe was still young, and the time for gas to gather and cool down into stars was relatively short. Another intriguing feature is their massive stellar mass, around 1 billion times that of our Sun. This suggests they managed to form a hefty chunk of stars in a short amount of time, something that current models struggle to explain. So, what could be causing this cosmic kerfuffle? Well, there are a few possibilities on the table. One is that these galaxies are undergoing a supercharged phase of star formation, a bit like hitting the fast-forward button on cosmic evolution. This could be due to factors like a burst of gas inflows or collisions with other galaxies, providing the fuel needed to power such intense star formation. Another explanation could be that these galaxies are housing particularly massive and efficient stars, leading to a higher luminosity and stellar mass than we'd typically expect. But perhaps the most exciting explanation is that these galaxies are pushing the boundaries of our current understanding of physics and cosmology. Maybe they're revealing new processes or phenomena that we haven't accounted for in our models, such as exotic forms of dark matter or interactions between ordinary matter and dark energy. These ideas might sound like something out of a science fiction novel, but they're not beyond the realm of possibility. The discovery of galaxies like Glass Z12 and Glass Z10 is a bit like finding a hidden room in a familiar house. It's a reminder that there's still so much we don't know about the universe, and every new observation has the potential to rewrite the cosmic rulebook. It's an exciting time to be an astronomer, and we can't wait to see what other surprises the cosmos has in store for us. And there you have it, a cosmic journey through the wonders of the universe, from the super-Earth exoplanet TRAPPIST-1b to the ancient galaxies of Glass Z12 and Glass Z10. Each discovery reveals a little more about the vast tapestry of our cosmos and challenges us to rethink what we thought we knew about the universe. So, next time you look up at the night sky, remember that there's a whole universe of secrets waiting to be uncovered. All we have to do is keep exploring.